All right, so it was on. It was working. It was working when she was using it. So I'm talking about something a little bit more with more physics in it, basically, in the sense that we're not solving physics problems with machine learning or machine learning with physics, but we're trying to put the two together to do design of imaging systems. And this idea of computational imaging is the idea that you should design imaging systems in such a way that you think about both the hardware and the software together. So if something's best done by optics, do it with optics. If it's best done later in computational post-processing, do it later. And so it's not just image processing and it's not just optical system design, but how the two interplay with each other. So I think of this as having two pieces. You have your image system design piece. This is like the optical engineering. This is more of like the black art of trying to design physical systems, putting together components, and trying to map something that you're trying to image, X, into some measurements, Y. And so the second piece of this is solve for X, and this is the computational part. But the heart of computational imaging is the interplay between these two, that we iteratively design back and forth between what's best done by hardware versus software. And I want to give a concrete example to start. So this is the canonical lensless imaging problem. You just take your camera and you remove the lens, and so it's just a sensor pointed at the world. I take a picture and it looks like garbage, right? But the light that hit the sensor is the same light that would have hit the sensor if the lens was there. The lens's only job was to bend the light in a particular way. And so if I could computationally bend the light in that particular way, could I take this image and reconstruct my scene from it? The answer is essentially no in practice. But so what we've designed is this, what we call diffuser cam. We put a diffuser, which is just a bumpy piece of plastic. It's literally the stickers you put on your window so the neighbors can't see in. And you put this in front of your sensor, just sitting on top of the sensor. And you take a picture, and it still looks like garbage, but now it's a structured garbage. And from this image, we can use computation to get back our scene. OK, so this is a great example. You take an indirect measurement, and you computationally reconstruct the scene, but you designed the physical hardware knowing what you were going to do in the algorithm and what was possible in the algorithm. So this diffuser cam is really fun. We have a whole bunch of them in the lab. You can build it on any kind of sensor. Better sensors work better, of course. This is the Raspberry Pi one. You can find an open source tutorial, hardware plus software tutorial on our website. You can make this with your kids on the weekend and then send us bug reports. So this is very different than traditional optical design. Traditionally, you're trying to image something X, and you take measurements Y, and you try to make an image system that has this forward model or operator A that is just the identity matrix. You want to map your scene to your sensor, right? With computational cameras, we're not after that anymore. What we want to do is map the information from the scene into the sensor, and it's usually done in a very multiplexed way, meaning that a point in the scene maps to a lot of pixels on the sensor, not just one single pixel, and we're going to computationally untangle them later. So to do this, of course, this is a simple linear problem. We're going to get into nonlinear problems later. But to solve even this linear problem, you need to know this matrix A. And if you think about this diffuser cam, we have a 5 megapixel sensor measurement. We're trying to reconstruct 5 megapixels of the scene. So A is 5 megapixels squared. We need to either know it, model it, or we need to measure it, or model it, or learn it, because we need to know this A. We would also need to invert something like this, which is insane computationally. This is not something you could do at home with your kids on the weekend. And so we think hard about how we can design the optics to make this A structured in such a way that it need not be just a totally random matrix. So that actually is true. It's a convolution matrix in this diffuser cam case, meaning that it's completely represented by a single 5 megapixel image. So, but in general, we can think of the inverse problem to solve this is as an optimization problem. So minimize the measurement that you made, subtract the measurement you would have made given the current estimate, and then update that estimate. So I'm going to call this the model-based reconstruction. And this is traditionally how we've always done things, is to put it into these sort of optimization problems. This is like the classical, or people have given it different names all over today. But you take in this measurement, run your compute, and get your image back from it. So it's a nice, compact, cheap camera. Here's a much prettier image. And of course, it's single shot, so we can do videos. And the video highlights some of our reconstruction artifacts that we're getting here. So this would be a great way to reduce the form factor of your iPhone camera lens, but it's also has some work to go to get the high quality that we need. But we can also do interesting things with it, like get super resolution or fast imaging. But what I want to talk about is our inverse problem strategies. And this sort of optimization approach using the physical forward model is what we call this physics-based. We use some sort of optimization method to solve it. And there's a lot of people looking into, maybe I can just deep learn everything and forget about knowing the physics. I don't need to know the imaging system that I made because I can just learn it by putting in enough training examples. There's a lot of pros and cons to these. The physics-based is very interpretable and robust, but it can be slow. And in our case, we have these artifacts because we're modeling the physics as we thought we built it, but it's not perfect. And so inconsistencies, like if our diffuser thing melts a little and changes shape from after calibration, it can cause problems. So it does have this model mismatch artifacts that I think somebody called discrepancy something or other this morning. If you just deep learn everything, then it can be really fast reconstruction. That's super useful for practical imaging, but it's very not interpretable. And I don't really like this idea of just throwing away physics that we know. I spent a long time learning physics. And so what we're going after is this middle ground. How can we like efficiently build systems that know what they know and learn what they don't know? And we've heard a lot about this today. So I was really excited to see some similar concepts in totally different spaces. So our version of this is to take our iterative model or physics-based algorithm and unroll it. So we have a neural network where each layer of the network is one iteration of our of what would have been our iterative algorithm. And essentially, I like to think of this as the architecture of the neural network is now designed by the physics of the system. And it becomes a very efficient system. In some cases, we can get away with a lot less training data, or we can just get better results, as you'll see. So it makes a very efficient network. But we still need to train it. So we built a setup that does training, super simple, just a camera with a lens and our diffuser cam both taking a picture of the same thing on a screen. We just use a screen so we can change the image really rapidly and take a lot of images. And we do all this training overnight, and then we can run this thing using our physics-based network. So here's just some results. So that's the input image that I take in. And so our old methods are these physics-based ones, have these artifacts. And we're not exactly sure where all of them come from. Otherwise, we would have solved them by putting them in the physical model. And then the deep learning one is worse than this middle ground one because it just doesn't have enough to learn everything. And it also requires a lot more training data. So this is a good, and there's a spread of how much middle ground you want to take here. Christina has the only poster here on this, and she's in the back if you want to talk to her about it. She knows all the details. So because I wanted to give a flavor for computational imaging for a lot of people who've probably never seen it before, I'm also going to talk about one other hardware setup that we have in the lab. So we do a lot of microscopy. And this is a completely different hardware setup, but you're going to see some similar concepts. And this hardware setup is a plain old regular biological microscope with one hardware change that we've removed the illumination unit and replaced it with an array of LEDs. We can program how light is illuminating. Our sample's sitting here, and we have this LED array that's programming illumination angles. So if I turn on this central LED, it illuminates on axis. If I turn on this one, it illuminates off axis. So we play this disco pattern, this carefully designed pattern. And we can do all kinds of things with this single hardware platform. Probably the coolest computational imaging thing we can do is what we call this, it's called Fourier tachography. But the idea is that just like any microscope, we have to choose between field of view and resolution. So in this case, so I could zoom in on something and get really good resolution across a small field of view by using a fancy microscope objective. In this case, I've chosen to use a microscope objective that has a big field of view, but then it has terrible resolution. So we're not resolving the smallest features. I do this disco flashing of the lights, and I take these images at the camera. This is good because they're different images every time I change the illumination. They're all low resolution images, but all these images together can be computationally reconstructed into an image that's about 7 times higher resolution in each dimension. And so we're starting to do these very large space bandwidth product experiments on cells where you're looking at thousands of cells at once, but with resolution to see subcellular things happening. This is a cancer cell dividing. It's going to split into 4 other cells. And this is a quantitative phase image. I could end the talk here, but I'd like to get into a little bit of our dark secrets. And this is really fundamental to computational imaging, is that, so say we just have this nice linear problem. This A matrix is something we think we know it because we know the physics. We designed it, so we know the optical design. But in practice, we spend like half our lives doing calibration. And there's usually that one expert postdoc who can tune the duct tape just right to get the image in alignment, take the picture, and then somebody sneezes and it never works again. So we're trying to do reproducible science, and this is not reproducible science when only one person in the world can really like calibrate and tune these things properly. So we want to go after this problem computationally. And we call this algorithmic self-calibration. I also heard this called by a different name earlier. But it's this idea, and this is now a nonlinear problem. We're doing a phase retrieval problem for this super resolution stuff. But we know what's wrong with our system. It has aberrations, and these LED positions are always a little bit off, and it causes problems. If we don't calibrate, we get garbage at the output. And so we don't want to have to calibrate this thing. We don't want people to physically have to be experts in optics in order to get this thing working, because we want it to be simple and cheap and easy. So the physics-based or model-based way of solving this calibration problem is just to do a joint optimization, to optimize for both the x that you're looking for and these calibration parameters theta, which are a function of, which make our forward model sort of a function of these calibration parameters. And this has been really successful for us in being able to successfully get good quality images. We can do things like solve for this super resolution image and the aberrations in the imaging system all at once and digitally remove them based on that. So the last piece that I'll mention, which gets into this physics-based learning, is that we're using this now for this system, not for reconstruction, but for design of the imaging system. What should the LED flashing lights look like? So our heuristic design is based on our knowledge of the physics. And we did pretty well with the heuristic design, but these learned designs do better, and we can use fewer of them to get the same quality of images. So I'll just show one last result, a traditional measurement versus our learned designs only needs 2 measurements to get the same quality of image as like 69 measurements in this particular case. It particularly picks up the low spatial frequencies in a way that the traditional one just doesn't. So my last piece is that I'll talk about that optics and computers should talk together more, but I think because we're at this workshop, I'm thinking about machine learning and physics should work together more. We shouldn't be talking about which is more important, which we should do both. Thanks.